And this was a formal proof, a derivation, so if it's enough for you, that's okay. But if you want to see a graphic representation, just watch along this video. So here we have everything we need for this visualization. So we will take the simplest possible distribution that we can get. So the height of football players in Europe, the mean value 180 centimeters, standard deviation 10 centimeters. We will take the smallest sample so we could visualize it, the sample of 2 players. Okay, from the same distribution. This distribution is the same as here and the same as here. So what does it mean? What a dot means? Let's say we have Ronaldo. We picked Ronaldo as a first player and he's on somewhere on that line, and we picked Neymar on as a second player. So this dot represents Ronaldo and Neymar, 2 players, sample of 2 players, okay? And what we can see here is that we are curious about average of them, average height of them. So Ronaldo plus Neymar have 180 centimeters, 185 plus 175. But all the players in this line have the same height. So you'd have somebody who's 190 and 170, and they have average height of 180. Okay, and we can project all those values into this new line. Let's call it ON, of new axis. Okay, and if you would cut this new line and rotate it 45 degrees, we would get this graph. Okay. And remember, it doesn't matter if you have player 185, 175, 190, 170, 2 meters, 160. We only care about the projection of those points onto that red line. Okay, so we have a dimension reduction from 2 to 1, and I will talk more about dimension reduction in PCA and covariance matrices. So subscribe if you want to see it. But for now, just understand that we don't need 2 information, we only need 1 information, okay? And in this case, from 2 dimensions, we are getting 1, the average value. This purple value represents people that on average are 170. Okay, and one more thing. Here we have no correlation. Remember, the dots are all over the place. I will link a correlation and covariance video in description, but just for you to know, there is no connection between those dimensions. If you choose as first player Ronaldo, it doesn't reflect on the second choice whatsoever. You could pick Messi, Neymar, Zlatan, whoever, okay? There is no connection. So what of it? If we rotated it and we have this projection here of those points, so that point would go here, that point would go here, that point would go here. We can see an interesting conclusion. The standard deviation of x-axis and y-axis is like this, 10 centimeters. But also here we have 10 centimeters. We kind of see circles here. And it's more visible when we look at probability function of those points. It's not a scatter plot, it's a probability function. When we look at it from above, we can see that in this direction and in this direction and in this direction, we have the same standard deviation. It's also visible when you look at it from the side, okay? The plot doesn't really change shape. So we have the same standard deviation. And isn't that something else that this formula say? Because this standard deviation of a sample should be smaller than the standard deviation of a population. And it is, because this new axis is scaled improperly. Okay, it will be clear in a moment. But this new scale is a mix of 2 dimensions, of this one and this one. And it's kind of a new thing that we don't really know the size of. The only thing we know about this new axis ON is that the mean of it, the average value, is 180. Because if you pick 2 players, the average value the expected value of it is 180. Okay? So this line's supposed to be 180 centimeters, like this line, but it isn't. It's longer, and you can see it here. Okay? Here we have 180 square root of 2. And here we have 180 from Pythagoras theorem. Hope you see it. And remember, this Pythagoras theorem works for multiple number of dimensions. For 3, so a diagonal of a cubic, or for any number. 15,000. Okay, so what we want to do is, we know that the correct value is 180. And this value is 180 square root of 2. So we have to rescale it to a proper size. The proper size is 180. So we have to divide it by square root of 2. And then we will have 180, but also the standard deviation will shrink. And here we have a visual representation of how it would look like. So this red this black distribution is this normal distribution that we have here. And this red distribution is our new distribution, okay? Maybe I will write it. Here is this normal distribution, and here is the same normal distribution, okay? And you can see that this line is longer. We have 180 here and 180 square root of 2 here. What we need to do is we need to shrink it to a proper size. So this value here would be at 180. So we shrink it, okay? What we can observe is that we are now at the correct value, correct scale, but our standard deviation got smaller too. So it's now not 10, but 10 divided by square root of 2. And we can see that this is a bit smaller than this black one, okay? And remember, it works for multiple dimensions, so not only 2. If you would pick a third player, sample size of 3, so you'd have Lewandowski, Neymar, and Ronaldo, so Lewandowski additionally, you would have this distribution in 3D. And you would still could project all those points onto that red line, the new axis. And you can see that the standard deviation is the same here because it's kind of a ball. The points made a ball. A standard deviation in X, Y, and Z. So 3 players. But this value, look at this as a cubic. This diagonal is equal to square root of 3 multiplied by this side. Okay? And you could see it here. So in this case, if you would sample size of 3, we would divide it by square root of 3. And you can see that it fits the formula. It's just square root of 2, square root of 3. It's simply square root of n. Okay? But we have to notice something. We took the simplest distribution, normal distribution. When it's and it's obvious here that we have a standard deviation of this new axis equal to standard deviation of old axis on the graph. It's on the graph. In reality, it's bigger, but on the graph it's the same. But if we take different distribution, like yearly earnings in a city, in Tulsa, this distribution is not normal. But still, standard deviation here and standard deviation here and standard deviation here is the same. I hope you could see it. The shapes are not exactly the same, but the standard deviation is. Okay? Here we look at it from the perspective of this diagonal, and here we look at the perspective from the basic distribution. So there we have it, a visual interpretation and formal derivation, the proof, to understand how standard deviation of samples work in CLT. But there's a lot of more to learn for CLT. We got this covered, but what we have left is how we can use CLT in real life, and we have to learn those subjects, and I will cover them in next video. And if those videos are not uploaded yet, I will upload them soon. And if you liked this video, maybe give me a thumbs up, maybe a subscription to let me know that you like my content and you want me to cover more subjects from machine learning. Thanks for watching. Bye.